Thank you, Keegan. It's my pleasure today to introduce this morning's keynote speaker. Dr. Aleatha Parker-Wood is the machine learning and algorithmic privacy lead at a startup called Humu, which is a really interesting startup that brings together analytic rigor and psychology and analytics together for improving the workplace conditions. Prior to Humu, she was the senior principal research engineer and manager of the, and note the acronym, Center for Advanced Machine Learning, CAML, right, at Symantec, where her team did original research and contributed machine learning models to numerous Symantec products, including many of you may have heard of, like SEP14, email cloud security, Norton Core, phishing page detection. She holds many security-related patents and serves on the steering committee for several other conferences of this ilk, like Skynet, the Security AI Networking Conference. She received her PhD in computer science from the University of California, Santa Cruz. I came to know Aleatha through some of these other conferences. She has been a champion in our community for bringing together especially the rigor of academia with kind of like the brutal reality of where we are in InfoSec. And I think she is no one better to kick our keynote off on that note than Aleatha Parker-Wood. We're lucky to have her today at CAMLIS. Please join me in welcoming Aleatha.
Thank you for that glowing introduction, Hiram. I'm really, really excited to be here in front of you, and I want to talk about an issue that is underrepresented in the security space, which is talking about privacy, and in particular when security and privacy don't play nicely together. So I'm not going to call anybody out here. This is our day-to-day reality. This is the marketing speak that lands on all of our pages. We correlate trillions of security events. We store, index, and classify all network traffic. We continuously study people's inboxes. This is really, really sensitive data, and this is a huge burden of responsibility. Modern security runs on data. We need to be able to do malware detection. We do anomaly detection. We do graph analytics. We may do deep packet inspection, and of course, we always need to do forensics. That's a perennial classic. To make things worse, the attack surface is expanding. We're now dealing with BYOD. We've moved from classic firewalls and network models to zero trust. DLP now needs to cover third-party systems and vendors. And not only do we need to worry about spam, we need to worry about email spoofing, we need to worry about social engineering attacks, and now apparently we need to worry about deepfakes. To effectively protect our users, we need data about everyone and everything. Unfortunately, now you have more problems. Here are just a couple of examples of places where the data that was collected for security purposes was either misused or became a tempting target in its own right. VPN hacks, the Yahoo hack, Facebook and Twitter both taking data which was intended for security validation purposes and using it for ad placement. So any data that you collect for security is going to be subject to internal misuse, either legitimate internal misuse. Legitimate's a little bit of a strong word, but your marketing department wants their hands on it. Your ad placement department wants their hands on it. You still have insider threat problems. You have external economic attacks, and of course you have nation states who would also love to get their hands on a rich trove of data. So the question is, having collected all of this data to protect your users, are you still protecting your users? Or have you put them in harm's way by doing this? There's this adage that's floating around the internet which says that data is oil. I want to push back on that. Data is absolutely not oil. Data is a barren plot of land that you have purchased, hoping that maybe you're going to hit oil. Maybe you're going to get value out of it, or maybe you won't. As data scientists, you know that 99% of the data that we get is absolutely useless for building and tuning models, and we could just throw it away. The problem is we don't know which 99% until we build the model. In the meantime, that data is expensive to store. If you don't want it misused by the marketing department, you shouldn't be mixing it with non-security data. You should have very strict tackling on it. It's hard to protect it. It comes with legal and security burdens and risks, more so now that we are living in the age of GDPR and CCPA. We have a bunch of new responsibilities around how we handle user data, and it's an attractive nuisance for every nation state and script kiddie that would love to get their hands on it. And to add insult to injury, your ML model is also part of your attack surface. So as you build these sophisticated models over the top of your data, that also becomes a target. Of course, the traditional solution to protecting data is you have this nice hard shell with an intriguing inside. You're using encryption at rest and at transit because you know that's best practices. You're using access controls. You're using firewalls. And because this is 2019 and we work in the security world, we know that we can do defense in depth. We can do continuous authentication. We can do anomaly detection. We can do graph analytics. You see the cycle here, the escalation. You can't store enough data to protect all of your data with 100% confidence. You can bring the risks down, but you can never fully protect the data that you've collected. So again, you need to worry about internal misuse and insider threats. You have to be concerned about data breaches. You need to worry about model inversion and data extraction attacks where your ML model is actually used to extract information about your users. And of course, you have, unlike a lot of other machine learning domains, active adversaries and adversaries who are interested in actively poisoning your data set. In an ideal world, we would have exactly the data we needed. We would have thrown away that 99% already, and we would have it at the right moment. We would have nothing more and less. We would have security for all of our users, but we would also have privacy for all of our users, except obviously for the bad ones. The problem is that we still don't know which ones are the bad ones, and so we need some sort of a balance between security and privacy so that we are protecting the users whose data we're collecting while still being able to find the bad guys. In this keynote, I'm going to spend some time talking about what your options are for privacy-aware machine learning. What techniques are available? How mature are they? What sorts of attacks are they going to protect me against? And most importantly, because a lot of these things are just coming out of the theory domain, what do we know about how they work in the real world? I'll spend some time talking about some familiar favorites like incremental learning, just as a warm-up. I'll talk about private multi-party machine learning, differential privacy, and then I'll spend a little time wrapping it up at the end, talking about when all else fails and you really do need to collect all the data. So incremental learning and sketching is one of the first places that data scientists turn when they don't have either enough storage to store all the data or they have other reasons why they can't retain it. So one popular example of this is a Bloom filter. Sketching means you're going to learn summary statistics as you go, and you're going to throw all of the data away. So you're basically running the data through a streaming pipeline, calculating stats, and tossing it. So the familiar favorites in this area are things like Bloom filters, rolling averages, maybe something more complex like count, min, sketch, or hyperlog. These are usually descriptive. They're not great for prediction, so you're not really building a machine learning model, you're just taking statistics off of the stream of data that you have. But the nice thing is that because you are throwing the data away as you go, they're mostly robust against insider threats and against breaches because you're not actually storing anything. This is an extremely mature area of research. It's very storage economical, and most of industry is already familiar with it and knows how to use it. You have a lot of these algorithms out of the box in things like scikit-learn. Slightly less familiar are things like online learning, where you're doing incremental model updates in the face of new data. There's a lot of work in this area, and this is also fairly mature, but it's not as popular. So, for example, there are online versions of decision trees, such as Hufting trees, which you can use to learn incrementally on a stream of data and throw the data away. For deep learning, stochastic gradient descent is kind of naturally online, although you can't iterate back over the mini batches that you've used, so you do need a continuous stream of data. And most of the deep learning algorithms that are out there are easily adapted for streaming data. The thing that's tough about this is it's difficult to do model selection. So as data scientists, let's assume you're getting started as a data scientist, you've taken some grad level courses, you know a few things about how to do this. What you usually do is you sit down with a data set, you have the entire data set in hand, and you say, okay, I'm gonna run 5 different types of models against it, I'm gonna see what sticks, and then whatever sticks is what I will implement into production. Working with streaming algorithms takes that ability away because you can't go back to the original data and you can't retrain your models. So you either need to take the risk of pushing a bad model into production, you need to run multiple models in production, or you need to have a period of time where you are in fact collecting user data with all of the risks associated with that to train your model before you push it. When is incremental learning not the right answer? Both of these only work when you have good assumptions around the underlying distribution. And in particular, a lot of online algorithms have assumptions that the data is stable. You don't have concept drift, you don't have an active adversary, the data is IID. All of these things that as a security person you know are absolutely not true about the stream of data that you have coming in. So this is really suitable for things where the vast majority of your users are normal, and then maybe you're looking to do something like anomaly detection. You still have problems with model inversion attacks, that's still a possibility. Data poisoning attacks for sketching algorithms are actually really, really actively researched. I think there was an entire session on it at IEEE S&P this year. So if you are looking to use sketching, there are defenses out there, and you can pull them from the academic literature. They're pretty mature. And if you want a free research area, it looks like nobody has done a lot of research on how to poison things like streaming hafting trees. So, you know, if there are any academics in the audience that would like to work on that, it's worth taking a look into. The next thing I'd like to talk about is differential privacy. This is an area that I got really excited about 2 years ago, in part because it has some very nice benefits for your machine learning models themselves. I'll talk a little bit about that. So differential privacy is an information theoretic privacy guarantee. You use carefully calibrated statistical noise to cover one person's input into your statistics. So you can always guarantee that an individual's data can't be extracted back out of whatever model you've learned. There's this parameter, epsilon, which describes an upper bound on the difference of two probability distributions, the one in which that user is present in the data and the one in which they're not. Some implementations also have a parameter called delta, which I like to think of as the O parameter. That is the possibility of full and complete disclosure of somebody's data, so you have no information theoretic security. So some differential privacy implementations can fail catastrophically for some users. So just to give a very lightweight example of how differential privacy works, let's say that we're in this building. I know we are a little over capacity for this conference, and I'm really concerned about the floors in the building because it's a little bit older building. So I want to know if we're exceeding the weight limit. So if I ask you how much you weigh, and you how much you weigh, and you how much you weigh, that's incredibly rude. I would never do that. But if I ask each of you to give me your weight plus or minus a Gaussian with a fairly large variance, you have plausible deniability. So each of you can report your weight to me, knowing that you have, some sort of deniability. But if I take all of that and I aggregate them together, I'm going to wind up with something that's approximately the true mean because I'm adding unbiased noise and it's all going to come out in the wash. So this is really, really nice. In theory, it's incredibly easy to understand how this works. Not so much in practice. So in a nutshell, you can think of this as taking noise, building it over top of itself, and as you add more and more noise, the true data starts to emerge back out of the data. But if you take any individual piece, what you're going to see is something that looks very much like noise. So I'm going to talk a little bit about a slightly richer example. This is something that we've been doing at HUMU to protect people who are taking surveys. So let's say that I work in the evil empire. Emperor Palpatine is in charge of the entire organization. Padme Amidala has been conscripted to run engineering, and Anakin Skywalker is running sales because he's a very charming man. So let's say I report out a couple of things. I report out response rates, so I know how many people in each organization have actually responded to the survey. And I want to do this because I want to encourage people to take the survey. And the other thing that I report out is something which has some aggregate statistics about those responses. So I might say that, for example, engineering feels very poorly about working for Emperor Palpatine, whereas sales, if they would actually answer their surveys, might love it. You never know. The thing I want to prevent here is being able to take multiple sets of reports and difference them so that I can extract responses for one individual. So for example, if I know that no one in sales has actually answered the survey, I have a copy of Padme Amidala's report, and I have Palpatine's report, then I can say with confidence that if I take the difference of those two, I know exactly what Padme had to say about working in this organization. So the way that we protected our users against this attack was by adding noise to the response rate. So you could never be certain how many people had actually responded to the survey, and therefore you couldn't figure out whether any individual was actually in the survey data or not. The thing that's interesting about this problem is that the attack only works at survey close. So at the point at which you roll out the reports, that's when it's possible to know who said what. But because survey respondents are coming in over time, we don't know when that last point is going to be. We don't know when the last respondent will show up. So we have to stay in a private state at each time point. And finally, we also want to make sure that our survey response rates don't go up and down over time, because that's just a very strange user experience. So the solution is to use something like a high watermark, where you draw a number from a noise distribution. You check to see whether it's larger than the previous draw, and if it is, you move the high watermark up. And if you don't, then you leave it at the previous number, even if that number is smaller than the true response rate. So by doing this, by adding just this little bit of noise at each step, you can cover up individuals' responses, but you can do it without compromising the user experience of understanding how many people have actually responded to the survey. And what you wind up with is something that looks a little bit like this, where you're very consistently over-reporting just a little bit. So the true response rate is the blue line here, and then the yellow response rate is what we're actually reporting back to the customer. So some places where differential privacy is being used right now. It's used a lot for things like reporting raw statistics. So I don't know how many of you have heard this, but the 2020 census, because the census has realized that they also have a significant privacy problem, is going to be using differential privacy to protect some statistics about the underlying populations. Apple has made a huge deal out of the fact that they use this for predictive text on the iPhone. I will talk very briefly in a second about why I'm a little suspicious of their claims. And then there's some more interesting stuff coming out of the academic literature about things like preventing model inversion attacks. So one of the interesting things about differential privacy is because you're covering up individuals' inputs into the training set, you can actually prevent things like overfitting. So you're not going to overfit on a single point because each point has been perturbed a little bit. And so you're not going to learn, if you're doing something like learning on a manifold, you're not going to overfit to that curve in the manifold. And there's a bunch of things coming down the pipeline in the academic literature about things like privacy for location traces using differential privacy. So this is actually a really, really powerful framework. It's got a lot of very nice characteristics. It's good at preventing model inversion attacks. It has strong guarantees about joining attacks and side channel attacks. And if you use something called local differential privacy, where you're adding privacy before you submit the data, so for example, you're learning on an iPhone, you're adding noise, and then you're sending the noisy data point to a training server somewhere else, then you don't have a problem with collecting user data, you don't have to worry about breaches, you don't have to worry about insider attacks. And early research in this area looks like it's fairly resilient to poisoning, again, because of this not overfitting characteristic that it has. The problem with differential privacy as a framework is that it's, again, an information theoretic guarantee, and the list of people who reason gracefully about information theoretic privacy guarantees is very small. So this epsilon parameter that I talked about previously, where you're bounding the difference between two probability distributions, it's very hard to go from that to I understand how often I'm going to release data about my users or how much harm I'm going to do to them. Another thing that you need to worry about is because you're adding this noise, and you need to add noise large enough to cover the entire range of your input space, it has a tendency to do things like suppressing outliers, which if you're learning in a security context, you might not necessarily want to do. So if you have a huge input range, or you're trying to calculate something that is in fact very sensitive to individuals, you might swamp all of the utility. There are techniques like condensed differential privacy, which add slightly less noise and protect sort of the the probability mass of your normal users and then expose outliers. So you can use techniques like this where you think that you're only concerned about people who are behaving normally and you really do want to surface these outliers. The last downside is that they're very data hungry. So because you're learning over noisy data, because you're deliberately learning over noisy data, you then need more data to be able to fit a model that's actually effective. So for many of us, that's not really a problem. You have trillions of data points every day. For other domains where you're dealing with very, very small amounts of data, like if you work in email security and you're trying to detect something like business email compromises, this is really hard. This is really painful constraint to work with. The next thing I'd like to talk about is private multi-party machine learning. So this is kind of a catch-all phrase for a bunch of different techniques. So for example, there's federated learning, which is about 4 years old, and this is the idea of doing distributed machine learning across mutually distrusting systems. So as an example, you might have a mobile phone, you're typing in text on your mobile phone, you want your predictive text to work well, but you're not typing enough data on your individual mobile phone to build a good predictive text model. You also would prefer not to have every single word you type sent to Google or to Apple in order to learn a model. So the idea here is that you're going to learn a model locally, or you're going to learn some statistics locally, and then you're going to merge that model with models from other devices, either centrally or via gossip protocols, and then you have some sort of privacy guarantees over the model that you're learning locally. So this is really useful in domains where you have regulatory issues about data locality. So for example, if you can't pull data out of the EU for legal reasons, you can learn a model in the EU, you can learn a model in the US, and then you can merge those together. So a couple of federated learning techniques that are available to you. I talked a little bit about local differential privacy, where you're adding noise to the data point before it's returned. This is what Apple claims to use in the iPhone, where they're adding noise to the distribution of words that you type. However, I mentioned earlier that it's very difficult to choose an epsilon. The parameter that they've chosen is, by academic standards, extraordinarily large, and they reset it every day, which violates a lot of privacy assumptions, so their information theoretic guarantees are really weak. But this is what they're doing. It's very fast because it's very easy to draw from a noise distribution, but you wind up with accuracy problems, especially if your individual local model is very sparse. If you're not using it a lot and you're adding a bunch of noise, then your information gets wiped out in the process of doing local differential privacy. And it's not always obvious within a given domain or problem the right way to determine how much noise you need to add. For simple statistics, it's pretty well documented, but as you go up in complexity, as you're doing things like trying to train differentially private models, it gets more complicated to understand how much noise is needed to protect a single user. Another technique that's very well researched in the academic literature but isn't used very widely in practice is secure multi-party computation, which usually involves a cryptographic protocol between two or more partners and a bunch of different exchange rounds. So it's got very different privacy guarantees, or very strong privacy guarantees and very good accuracy guarantees, but because you're doing this very complicated multi-round protocol, it's a huge amount of communication overhead. If you're in a situation where you have limited or flaky bandwidth, it may not work right. So there are good reasons why it's not used in practice, but it is a very nice, strong model. And one of the ways that it's commonly implemented is using something like homomorphic encryption, where you're calculating statistics over encrypted data and then returning the results of that calculation. So you're never decrypting the data, but there's still the possibility of doing side channel attacks, and in particular, if you have a poor choice of functions that you want to calculate over the underlying data, it's still really easy to release things that you didn't intend to release, and you don't have a lot of visibility into what's being done. There's some really interesting papers coming down the pipeline in this area, which are trying to mitigate some of the problems that I just talked about. So for example, there was a paper which I think is coming out at AISEC this year on a hybrid approach to privacy-preserving federated learning. So this one takes differential privacy, which I mentioned is fast and has accuracy issues, blends it with homomorphic encryption, which means that it is both more accurate than differential privacy and faster than using raw homomorphic encryption. Another one that's really intriguing is Papernau's paper on a private aggregation of teacher ensembles, where you're learning individual machine learning models on each device, and then you're using those to do a teaching process, a model transfer process to a publicly trained model. So you use public data to query the private model, get its predictions, and then you look at whether each of the private models agrees on the predictions, and where it does agree, you learn something, and where it doesn't, you throw it out because you assume that that used data that was private to that particular device. As a bonus, it comes with Byzantine fault tolerance, because if your device is very flaky and is spitting out meaningless labels or has been compromised, then it's not going to make it into the final ensemble. The trouble with federated learning is that there's, as I mentioned, a ton of research in this area, and it's not always easy to decipher what the trade-offs are between these different types of models. Everything is still very much in the academic literature. There's not a lot that you can buy off of the shelf. A lot of the research is only about 4 years old. There are some real-world implementations, so I think Pate may actually be used in the wild. I think it's getting used for Google Keyboard. But accuracy and efficiency are still both active challenges, and advances in this area are going to be gated by problems in mathematical theory rather than software engineering problems. So you need things like advances in homomorphic encryption, or you need advances in secure set intersection. So this is going to be a very slow field, but it's also a very promising one. When all else fails, sometimes you really do need all the data. So for example, you need to be able to do a full forensic analysis. So the thing that I would like to call for is to be extraordinarily mindful around what you're going to collect and how you're going to store it and who you're going to give access to it. If you're working with people's email data, please be sensible about who gets access to it and what sorts of things they can see. Even metadata can reveal huge amounts of information about what people are actually up to in their day-to-day lives. Make sure that your user understands and consents to all of the uses that you're going to put their data to, whether that's security purposes or marketing purposes or ad purposes. Don't surprise your users. That's how you wind up on BuzzFeed. Nobody wants to be on BuzzFeed. That's a bad day. And a change buried in your EULA is not protection against surprising your users. So you really do have to be very upfront. You have to use plain language about what people can do, what people can expect from you using their data. There's really not a silver bullet in this area yet. Not every system is going to need deep learning or blockchain, and not every algorithm is going to need differential privacy or secure multi-party computation. Private learning is a lot more challenging to implement than just importing sklearn, and there are no Coursera courses on it yet. But you have a whole bunch of options, so as you're thinking about how you can do security learning, it's worth asking yourself, do I need the data? How much of the data do I need? Are there alternatives that I could use which would allow me to give my users more privacy while still learning the things that I need? And figure out what makes sense for your users, your threat model, your regulatory environment. Maybe you do need all of the data. If you do need all of the data, be thoughtful about what you collect and how you store it and who gets to access it. And remember that at the end of the day, the reason why we're in security is to protect people and their data. So let's keep that in mind as an end goal. Please ask me questions so that Hiram doesn't have to.
Is this mic on? Okay. We'd like to take some time for questions. If you'll raise your hand, I will give you a mic so that our streaming audience can also hear.
Thanks. It was a great talk, very clear actually. And my one question, rather concern about this differential learning, right?
Differential privacy? Yeah.
Privacy. So you kind of create sort of boundaries of what you define as a noise or not, right? But often you get outliers, right? And well, you decide that this is enough data, but then you get more data as changes survey techniques, and your outliers turn into an island that grows bigger and bigger, and you realize that this outlier actually contributes to your model even more than everything else. It's maybe most important part. So aren't you scared that those models that you define could actually put boundaries on the society, right? And they will not, the conclusions will be wrong. Like in those case of those algorithms that predict, whether a criminal or not, if you've heard of those, right? And they made a lot of mistakes because it's just a program, right? So isn't it a problem of actually improving the survey statistics rather than improving the model, the actual mathematics of that analysis of data? I don't know.
Sorry, improving the which statistics?
The survey and acquiring the data, removing the bad data.
So I would say if you're cleaning your outliers, then you certainly have a problem. If you have kept the outliers, so let's say you're doing local differential privacy, it's true that the privacy algorithm is going to add some noise, so those points are going to jitter around, but if there are in fact a lot of them, then you're going to start to see probability mass landing in those areas over time. So if you really do have a big problem, you have this island of outliers, then you are going to see that start to come out of your data. But again, you're going to need more data to see it than you would have before, so your learning process is going to be slower.
Good talk. Learned a lot of stuff there. So one of the things that I had a question about was when you were talking about differential privacy, you mentioned that the models tend to be very data hungry, but security, for the most part, we have a lot of data. But I was thinking that even though we have a lot of data in security, one of the problems we still have is the class imbalance. So my question is, wouldn't that exacerbate class imbalance? You use a differential model that was data hungry because you don't have that many, that imbalance, or the class that's not represented as well.
Yeah, that is definitely a concern. So when you have rare problems, so in some problems you have class imbalance, and other problems you don't. So for example, if we think about malware, and you look at all the malware hashes that are out there versus the amount of good software, you actually have huge numbers of exemplars on both sides. If you're talking about something like business email compromise, where there's maybe 100 or 1,000 examples, then you absolutely have a problem. One possibility is that you can learn a model for what normal data looks like, and then you can feed back in this rarer class. So let's say you have multiple data feeds, you have ways of getting raw data for, like a bad email, for example. You can feed that back into the model without adding privacy to it. So you can sort of use this hybrid approach. Does that make sense? Yeah.
Aleatha, I'd like to ask a question also. So I think most of us as users of security and in many cases vendors of security have come historically from a background of there's no expectation of privacy because we need the data in order to detect the bad acting. So this is a little bit of a paradigm shift that's happened over the last maybe 7-10 years, right?
Mm-hmm.
What, for everybody in the audience, what is like the simplest? So we're probably less likely to rewrite our deep learning model to have federated learning incorporated because that's a heavy lift. But what's the simplest thing that I can do as a vendor to kind of embrace with my existing technologies privacy? So think about UEBA or think about like DLP or things where I'm ingesting documents or looking at links or web browsing history. All those things contain privacy information, and we have been sort of on a hunt to find the bad guy to chase us. What's the simplest thing we can do to not compromise security, but still preserve privacy?
I would say the simplest thing that you could possibly do is, especially like the previous questioner was asking about, in cases where you have a huge amount of data imbalance and you have labels. Let's hope you have labels. But let's say you're doing DLP and you know that the vast majority of these documents are good documents. Just start doing things like putting in sensible data retention policies where you say, if I have good documents, I'm going to keep them around long enough to learn from them, and then I'm going to discard them. Like, don't keep good data around. Don't keep benign data points around longer than you need to learn from them.
Thank you. Aleatha, thank you for the wonderful keynote introduction. Let's thank our speaker one more time.